I'm Breandan Considine, as Paul mentioned. I have a background in computer science and machine learning. I worked for a few years out of college at a small startup. We did ad tech, and it got me interested in machine learning. So I spent another 2 years as a developer advocate at JetBrains, where I built developer tools and stuff like that. And I'm very interested in machine learning. I've been interested for quite some time, and it's a very rapidly evolving field. So I think it's very exciting. And I built some tools for speech recognition. You can check them out on my GitHub page. I enjoy writing the code, going to conferences like these, and I hope to meet some of you afterwards. Feel free to say hello. This is my social contact information. Let's see. Okay, so today we'll be talking a little bit about TensorFlow. TensorFlow is a framework built by Google, and it helps do lots of things, including machine learning, deep learning. So we'll talk a little bit about that. And if you have any questions, feel free to interject. It's kind of a workshop, so we'll answer any questions as you go along. So you may have heard of tensors before. Tensors are kind of, they're intimidating a little bit. So it's simple enough to think about. Tensor is just an n-dimensional array. There's a joke. There's some mathematicians and an engineer and some physicists at a conference, and they're talking about string theory or something like this. And he says, oh, well, you know, in this, we have 26 dimensions or something like this, right? And the mathematician says, great. And the engineer says, how do you picture 26 dimensions? Well, that's way too many. I can't imagine anything that big. And the mathematician says, oh, well, it's easy. It's no problem. Just picture n dimensions and set n equal to 26. So it's sort of similar with tensors. Tensors are a generalization of arrays and matrices. So we use them all the time in just smaller forms. So this is a tensor. It's just a one-dimensional tensor. This is an array. And this is a matrix. So these are indexed by their rows and their columns. And you might notice a pattern. So in order to index something in an array, you only need one index. For matrices, you need two. And you can go up the ladder. So for an n-dimensional array, a rank n tensor, you need n numbers to index. And so we use these to represent lots of different things in mathematics and statistics. And they're good at capturing relationships between lots of different variables. So lots of the real data that we interact with on a daily basis can be modeled by a tensor. So for example, audio. In speech recognition, you can represent an audio stream in different ways. So there's a time dimension, there's a frequency dimension, and there's an amplitude. And you can transform, go from different dimensions by using something called an FFT, or fast Fourier transform. But this is essentially a very large tensor. So you can represent it as that. Images. Images is another form of tensors. So if you have an n by m image, then you can represent this image as a single point in a much larger dimensional space. So images in general can be thought of as just points in like a 1,000 or 1,000,000 dimensional space. And so by representing them as tensors, as arrays and matrices of objects, and doing some math on these, we can do some very interesting things. So we can transform these using mathematical operations. So this is an average face taken across lots of different pictures of faces. You average all the features, and you get something that looks like this. And so there's a lot of interesting research that goes into studying facial recognition. Some of it's kind of interesting and a little bit alarming, what you can do. So for example, if you have an image of a face that's smiling, it's probably a neat thing to do. You can try it out. You can apply an operator to move from a face that's neutral to a smiling face. So this is something, you can do this just with a simple tensor operation. So they're good for lots of things. You can model complex systems, lots of big data, and they capture a lot of data about the correlations between different variables. So you have all these different parameters, and some of them are related in interesting ways, and you want to capture those relationships. Well, we could represent this in sort of an object-oriented format and try to do a lot of manipulation with the variables to get everything we need. But with tensors, it's all there, and we just treat it as an encoding of a natural object. So it helps us do machine learning, and that's what we're here for. So what is machine learning? We can think of machine learning a little bit like a black box. So we have our inputs that go into the box, and we read, we look for different patterns in the inputs. And what we're trying to do is trying to predict something given a new input that we've never seen before. And we have control over some parameters inside this box. So the parameters can be like 1,000 different parameters. And you can imagine these as little dials in the box. And what we're trying to do is, given a new input in supervised learning, this is one type of machine learning, that we can kind of turn the knobs all in the right direction so that when we given a new input, we predict its class with high enough accuracy. And this is basically supervised learning in a nutshell. There are two types of supervised learning: regression and classification. And so if you're dealing with numerical data, regression helps us fit a line to a bunch of data that we have, a bunch of data points. And this is pretty classic machine learning exercise. So we'll go through a simple regression exercise in TensorFlow. And the second one is classification. And so they're a little bit related. Classification is used for discretely valued classes. So if you have like dogs and cats and you want to predict, given an image, if it's a dog or a cat, this is a classification problem. If you want to predict the price of a stock based on previous prices and things like this, and it's more or less continuous, then you can use regression. And the idea with regression is that you're trying to fit a line to a bunch of points, right? Or a function to a bunch of different points. So we'll take a look at simple linear regression. So so we'll use some frameworks to do that. We'll need to import TensorFlow. And we'll use NumPy as well to generate some fake data. And we'll use something to visualize our data, so something to plot it. Let's use matplotlib. Matplotlib. Okay, so we're going to need some training data to try this out. So we'll generate some training data, and then we'll use this to train our regression algorithm. So let's see, we need some training data for x. And we'll generate a bunch of points from -1 to 1, say 100. And we'll generate some y's. So let's do like a line with a slope of maybe 2. And let's see, so we're going to multiply this by x train. And we're going to do np. And let's see, let's do from 1 to 100 as well. And let's multiply this by 3, 3. Okay, and just so we can take a look at what this looks like. Okay, good. Okay, so we have some data here. It's two-dimensional data. It looks sort of linear. So let's, we see this data and, okay, well, we want to approximate a best fit line to this. And remember, our goal is to, okay, well, so I'll explain it as we go. So in TensorFlow, it's sort of declarative. So you don't, it's not an imperative sort of framework. So what we're going to do is we're going to treat it as some initialization variables, and then we're going to run these in a later loop. So let's see, we're going to need some x's, and this is going to be where we accept data. So x is going to be, we're going to put a placeholder here. And this is a floating point, or floating point number. And then we're going to create our y's as well. And now we're going to need something to model the x's and the y's. So we're going to do, put another operator in TensorFlow. It has a bunch of different mathematical operators for working with tensors. So we'll do multiply. And we're going to multiply something by something else. So what are we going to do? Well, we're going to need a weight. So this is going to correspond to the slope of the line we're trying to learn. That's what we call it. This is going to be a variable. So as we're learning, we're going to adjust this parameter and try to find the best one for the data. And we're going to say it's 0 initially. It can be random or 0, anything. We're going to figure out what it is later by fine-tuning it. Okay. And this is going to be our x's multiplied by our weight. Is our y. And then we're going to define a cost function. So a cost function measures how good of a fit our current set of weights is for the data, or how closely, it's also called the loss as well, so we could call it loss. And in linear regression, there's different types of linear regression, but we'll use ordinary least squares linear regression, which just says the cost function is the distance between the point that we approximate and the actual point in our data. So if we go back and look at this, if we draw a vertical line between one of these points and the line that we're approximating, the current line, then that will give us our cost. So we'll do here is we want this to be, we're going to try to minimize this. So we want this to be positive. So we'll do, we'll square it. And we'll take the difference between y and y model. Okay. So far, so good? Okay, so in TensorFlow, there's this thing called a session. And session is, it carries all of the parameters, and you're going to run this. The session encapsulates all the things about the parameters you're trying to learn. Maybe it has a neural net graph inside of it, or structure. And then with that, that session, you're going to initialize it and run it. So we've done the initialization right now. And now we're going to set up the session. So here. And then we're going to initialize all these variables. So right now, if we printed them, there wouldn't be anything there. So let's try. So it's just a placeholder right now. But once we initialize them, then we'll need to run this as well. So we'll do session run init. And we're going to, okay, so now the session is all the variables are initialized. We're using this session. And we're going to have a training loop. So this is where we train the slope, or the weight here, since it's only one parameter. So we're going to do, let's see, we can do this a fixed amount of times, or we can do this until it stabilizes. So right now, let's just do it for a fixed amount of time. Say 100 times. And then what we're going to do is feed it our training data that we've generated. So right now, we've initialized kind of the way it's going to work. All the operations are there in place. And oh, actually, we need to do a training operation. So it's a good thing I mentioned that. So we'll need to set a training op. And this is going to be, so we're going to do something called, we didn't talk about this, it's called a gradient descent. And this takes a parameter. So this is the learning rate. In gradient descent, there's a nice animation I can show you. We'll get to it a little bit later, but just to give you a preview. What it does is it starts at the initial point, where right now it's 0, and it's going to try to find the minimum cost inside of this function. And so as it's going to take small steps to do that. And the smaller the steps are, the longer it'll take. But the larger the steps are, you might skip over some minimum. So we want to make them kind of small. So initially, we're going to set this to like a really small number, maybe 0.01. So this will take small iterative steps to try to search around the nearby landscape and find the best minimum. And we're going to, let's see, minimize our cost function. Our loss, yeah, it's going to be here. Okay. And then we're going to, all right, so we're going to feed this data in. And we're going to do the, and we're going to feed it some data. So inside of our feed dict, we're going to call, it's sort of a convention. You call it the feed dict. And this is where the incoming data goes through. This is a map. And okay, so we're gonna run this, and then we're going to update the weights. So, good call. Thank you. Right. Because we're going to update the weights. And we're going to close the session when we're done. Right. Okay. So when we're done, we should have the final set of, it should be kind of stabilized by then. Let's hope it is. If it's not, we might need to run for longer. Wait. Thank you. Okay, so we've already, I'm going to show what this looks like at the end. And let's see, so we're going to need the final value for our model. And we can say this is, let's see. And we're going to need to plot this. Okay. Okay, let's run this and see what happens. Okay, so let's, I don't know if you can see this. Let's make this red. Okay, that's a little better. So, this kind of looks like a little bit like our data. This is the pattern we've found. We've learned the slope of this line, just given the input data, and we've done that through something called gradient descent. We don't really know what that is right now, but we've applied it, and it's trying to minimize our overall loss for the entire data set, right? And it turns out that we can run this again and show how the weight values kind of stabilize over time. So initially, the weights is not very good. So if we plotted this for each iteration, then we'd find that the initial weight, the initial slope of the line that we set isn't very good, and then we're kind of slowly approximating it through this algorithm. And TensorFlow is doing this all behind the scenes. So if we have a lot more data, like orders of magnitude much more, then it's all handled behind the declarative API, the interface that it gives you. So you could scale this on the cloud for lots of throughput. But right now, it's running on my CPU. GPUs are good. If you have a GPU, then you can use the instructions that are on the TensorFlow page to speed it up. And usually, you'll end up with orders of magnitude faster runtime because it's massively parallel. Right. Okay. So that was a quick taste of linear regression. So the next idea is classification. And classification is kind of an interesting topic as well, because most of the cool things that are happening with machine learning, with speech recognition, with image recognition and things like this, are kind of classification tasks. So we'd like to show someone a picture of someone's face and say, oh, this is Tom or Jim or Mary or something like this. And these are discrete values. So the simplest form of classification is called binary classification. And we have two classes. We'll model these as 0 and 1. And here we wanted to determine, given an animal's domestication and size, whether it's a dog or a cat. And the idea here is to draw the line not so that the line kind of approximates the data, but so that it separates the data as best as possible. So you want a line that gives you the best separation between the two classes. And so as you're going through, you're adjusting this line. You receive more training examples. And once you've received all the training examples, then you should have a line that separates the data as best as possible. So classically, you do this kind of in a very imperative way. So you have your classifier. What this does is it does a matrix multiply. So you you sum it all up, you multiply each of the weights by each of the inputs, you sum it all up, and then if it's less than 0, you return 0. If it's greater, then you return 1. And these are the two classes. And the training algorithm looks something like this. So you have some data, and it has some features. Here, there's 2, and it has a label. So it comes with a label. A lot of this supervised learning has to have labels in order to work well. And these have to be generated by a human. So initially, like, you could set it to 0. You could randomize the weights. And you want to run this until the total error is below some threshold. So while it's not, then we're going to keep iterating through every item in our data set and update the error and the weights and try to minimize the error. So it looks something like this. So you're going to take each of the input parameters and multiply them by a weight. It gives you and you take all of this, the sum of all those, and you're going to pass it through something called an activation function. And this activation function, there's different types, but it's usually a simple linear rectifier, or it's called you can use a logistic one as well. So you take the activation function, and this gives you the output. Right. So this is the output of the activation function can be a real valued number or a discrete value. And the threshold here is something that we set. And it looks something like this, again. So you have the two classes, and you're kind of approximating a line that separates them as best as possible. And this is kind of a toy example, but this is usually done in a lot of dimensions. So if your data is linearly separable, then all you need to use is this algorithm. And this is called a perceptron. Perceptron is the basic building block of a neural network. And so for many years, they use this to separate things and to do interesting work. But the problem is, classically, that it doesn't learn certain types of functions. And one of those is the XOR function. So if you have a perceptron, it will not be able to learn this just with one perceptron. So how do you get it to learn this function? Well, you need to kind of stack them together. And that was kind of the key ingredient, in addition to lots of hardware and big data, is that you take these little units, they're kind of inspired by the neuron, but it's a little bit different in a lot of ways, because it produces a real value output, and this is done using gradient descent, which probably we don't do biologically. So you stack them together, and you do this thing called backpropagation. And backpropagation, it takes all of the errors and then tries to update the weights so that for each layer, they're closer to what you'd like them to be for the next layer. And this is called backpropagation. Luckily for us, we don't need to know all this, because TensorFlow does this for us. So this is a single layer, multi-layer perceptron, and you have your input units, which are the parameters of the data. You have the hidden layer here, which does the dot product and passes them through the activation function. And then you have the output layer, which takes all of the outputs from the previous layer, and then gives you a single class, or it gives you which class it's part of. So it turns out that by stacking them up and adding lots of layers, you can learn arbitrary functions in high-dimensional space. We just kind of, we only recently, like in the last 5 or 10 years, we came up with some really good techniques for doing gradient descent with backpropagation. There's a lot of problems with getting the errors to propagate through lots of different layers. And until we did that, we weren't able to recognize images and do speech very well. Like we mentioned, this is gradient descent. And this function here you're seeing is the error surface. And you want to minimize your total error. And so it looks kind of bumpy, and it's hard to picture. But this is kind of an easy visualization in a small dimension. So there's lots and lots of different types of neural networks. They're constantly coming up with new ones. In fact, they're training neural networks to generate new forms of neural networks. And it's getting very intelligent about how you structure these things for particular domains. Just to give you kind of a quick taste of a neural net that learns the XOR function, let's take a look at that in TensorFlow. So I won't go through the trouble of coding it live for you. So there's a handy cheat sheet here. If I can. Okay. So initially, we have an interactive session. Interactive session allows us to evaluate. Oh, you can't see that, can you? Okay. So we're going to import, as we did before, and use the interactive session. We're going to, this time we don't need random data. We know what the XOR function looks like. And for classification, it's very common to use something called one-hot representation of the classes. And the way this works is that you have n classes. And then in order to model, to output a single class, you output an array of length n, or a vector of length n, and then for the class that you're predicting, you set it to 1, where you have an index for each class to a number, and then you output the 1. So here it's just binary for, let's see, so this is for 0, 0, it's going to be false. For 0, 1, it's going to be true. For 1, 0, it's going to be true. For 1, 1, it's going to be false. So we're modeling exclusive OR. And likewise, with the same way we did before, we have a placeholder for the x's and the y's, and we're going to feed this in. And here we will set a parameter called the number of hidden nodes. So this is the hidden nodes inside the middle layer of the multi-layer perceptron. And we're going to learn this weight. And this is going to be the same way before. Here we're going to have a bias. So in the last example, it was just some data centered on the origin. But here, maybe it is, maybe it's not. We're not sure. So we'll add a bias. This is how we model the hidden layer. We use this activation function called ReLU. It's a very classic thing to do. There's some math behind it. And then we're going to do the matrix multiply, and then we're going to add the bias as well, and then pass that through the logistic, the activation function to get the output. And so we're all just configuring the net right now. Right. So we're going to apply a gradient descent method called softmax. This gives us the same way we did before. We're going to define a kind of the cost function, or it's going to be called cross entropy, and we're going to apply that. So in our training loop, we go through the feed dictionary, we pass it in like we did before, all of the variables, and we're going to stop as if it's below a certain threshold. Okay, so let's run this. And are there any questions? Fair enough. So in this case, it takes very few iterations in order to work. Here we stabilize at around the 13th step, and we're completely accurate. Once we've learned the function, we're completed. So that's a multi-layer perceptron, and we've just learned the XOR function using TensorFlow. Okay, so let's take another look at something a little bit more complicated called MNIST. MNIST is a task that's used to classify handwritten digits. Handwritten digits are very useful. They come in lots of different shapes and sizes. And it's an open data set. You can get it from Jan LeCun's website. He developed this training set, and it has all kinds of labels for you. So it has all the handwritten digits. It's 28 by 28, and each pixel has a grade level value of 0 to 255. So if you, I don't know what you can do 28 by 28 in your head. It's a kind of a big tensor. And you need to learn for each class which you're given an image of a handwritten digit, like a 6, and you have to print out what the digit is. So just to give you a visualization of that, it looks like conference internet is not loading. So and there's a website here that you can go to. It's janlecun.com, and he has all of the performance metrics for a bunch of different classifiers, and they keep track of this year over year. You can download the training data to test a new model that you've built. And this, I'll put this URL in the links for you. So there's a great blog post if you want to read more about visualizing what these look like. But you see the handwritten digits here, and these are represented by a great big matrix with gray level values. And once you download it, it's all gzipped. You have to unpack it. But they're well labeled, and you can do some great supervised learning stuff on there. And if you go here, you can see some very interesting visualizations. This is Christopher Olah. He has a blog post about visualizing MNIST. If you Google it, you can see what it looks like. But you can think of all these points as lots of different points in a large dimension. And so if we map these points down to a smaller dimension, you can kind of see what they look like. So there's different visualization techniques. One of them is called principal component analysis. There's some others called TSNE, and these will map this high-dimensional data down to a lower-dimensional space while preserving the distance between each node that is, by preserving the overall distance. So for things that look similar, it will appear similar inside of the space. So for example, here you have a cluster of zeros, and they're all pretty similar. Far away on the other side of this projection is ones. So they look pretty dissimilar from zeros. Likewise, threes, they're all clustered together. And if you don't have labels, this is kind of a good way to get them. You can kind of compress them down to a lower dimension and then generate the labels using something called like k-means to get each of the sets. And there should be, so you can see they're kind of entangled here. There's a bunch of data that looks, if we can zoom in, let's see here. So it looks like 1s look kind of like a 5 maybe to this, and 6s, so it's a little bit entangled. But if you have good training data and good labels, then you don't need to do this. But this is a good way to visualize your data if you don't have an idea of what it looks like. And this is called t-SNE. Right. So this is pretty short. We're going to, so our model is 784. We're going to initialize these all to zeros. And we use cross entropy with softmax, the same way we did before. And we're going to reduce the mean of the error. So, so this might take a little bit longer. I actually haven't run this before. So I have the data, and it trains, I guess, so it did the training pretty quickly. So maybe this is probably a subset of the whole set. But a nice way to visualize, as you're training, is to use something called TensorBoard. And TensorBoard is included in TensorFlow. It's a neat little web application that you can go to in your browser. And the idea is that it gives you the average error over time. And so if you keep track of this, if it looks like the errors are kind of exploding or they decrease too quickly and you're not getting a good result, it'll sort of jump around, then you know that you're doing something wrong. So sometimes this may take like days or weeks, thank you, to train. And so to keep track of that training, you can use TensorBoard. It's a simple command line, and you have to write some data to a file. But when you do that, you can just run it here, and you give it to the path to your log directory, and then you'll be able to see nice little graphs of different hyperparameters and how the model is evolving over time. And this will help you iterate on these experiments a little more quickly. Okay, so it looks like we're coming to a close. I'll give you some further resources, and I'll post these online on Twitter when I go. You can check these out. They're very good learning resources for MOOCs, massive online open courses, and some visualization techniques you can use. Things to get more familiar with deep learning and neural networks. There's a great, this is by a great book by Michael Nielsen. And it tells you all about all these different techniques. And he doesn't use TensorFlow, but if you want to get a real handle on some of the math behind it, the math is very well put together. And gives you a very sound fundamental background of the techniques they're using. And I would highly recommend Andrew Ng's Coursera course on machine learning. That's available now. There's a bunch of sessions going on. You can check that out. So I'll post that online. I'd like to give a special thanks to our organizers, Python Ireland, for inviting me to come, and the TensorFlow contributors who created this great framework. A lot of it is a lot of the innovation that happens in machine learning is probably done behind closed doors. And of course, they didn't have to release all this stuff. Some of the magic is in the data itself, which is probably very secretly kept. But there's a lot of great open data as well. So you can check out open data sets and try to practice on them. And check out Kaggle.com. They have a lot of competitions for doing machine learning. And I'd like to give a special thanks to my family who's here today. They took some time out of their vacation, their holiday, to see me speak here in Dublin. Mary, Mark, and Margaret. Say hello. thank you very much for coming. And please feel free to ask questions. I'll be around for a while. Thank you.
So, yeah, any questions? The microphone.
Hi. So a lot of like online tutorials and stuff will go through like, training the model and then using the model. But in the real world, presumably, I would prefer to train my model and then at some later point actually use it to predict something. Is there like any specific way to like save a model for later? Or would you just like print the values and then import them again later? Like how would you do that?
Yeah. So we didn't go over serialization, but in TensorFlow, there's a very easy way to serialize your model once you've trained it. So you're learning these weights, right? And maybe these weights are lots and lots of weights. So you can serialize them to disk by using this command. Write to disk. Also, would highly recommend this book by Nikshant. It has some great examples for reading and writing data, and lots of other things. But you can find a quick example in here to serialize the data. I'm not sure if I can find it off the top of my head, but there's definitely an endpoint you can call in the interface that just says dumps the model to disk, and you can customize it to mobile devices as well. So if you need to run it on a low-power device like Android, and it's like a really big model, then you can compress some of it down to run on Android. So that'll, yeah, serialization is very easy. And there's also utilities as well for separating the training set. So typically what you don't want to do is overexpose it to all the data you have. So you keep like maybe 40% of the data hidden from when you're training the model. And you use that to evaluate the quality of your predictions later on. Otherwise, if you include everything all at once, then you might not have data to train it on real data, and you run the risk of overfitting to the data you have.